Hey there, it's Mr. Moydeen. Hope you had a good spring break. In this lesson, we'll be looking at the concept of area through the lens of calculus. So on the screen here, I have two pictures. Let's take a look at the left one first. You might have seen a picture like this back from maybe even elementary school. A question that might accompany a picture like this is, what's the approximate area of this blob, of this figure? And you would count the number of blocks, and then you would kind of estimate and say, well, looks like that these up here comprise one total unit and then fractions of units together, and you can get a good estimate. Of course, having smaller subdivisions gives you a better estimate. And more recently, we've learned how to do an infinite sum using infinitely many subdivisions, and that's called the definite integral. We're going to be finding the areas of spaces that look like this green blob here and finding the exact answer as opposed to an approximation. So how does this connect to what we recently learned? Well, last video we looked at the fundamental theorem of calculus, which allows us to find a numerical result for a definite integral by taking the antiderivative and plugging in the endpoints and subtracting. Now it's worth remembering that this element right here, this guy right here, represents the area underneath little f of x from a to b. In other words, that space is the same as this green space right here. So our task really will be to find the area under a curve, or as we'll see, between curves sometimes, as defined by this rule right here. To find the amount of space in green, follow this procedure. Now, it's not always as straightforward as we just saw in the generic sense. Sometimes you'll have multiple functions. Here you have a parabola g and a line f of x. And the task here is to find the area between these two curves. And the overall idea, that the nutshell of this that I don't want to hide, is this formula here. Top function minus bottom function. And you're going to integrate them from a to b, your left endpoint up to your right endpoint. Now, I want to take a minute here and just look at why this works just for a moment, and then we'll get to some practical examples. So I have my two functions here. F is the linear function and g is the parabolic function. Our task is going to be to find the area between these two functions, the exact amount of space there. Now, one way to do that is to first find this area here in blue. That's the area underneath f. So I can write an integral to find the area from a to b, a being the lower end point and b being the upper end point. Find the area under the blue function. Of course, that's too much. I need to remove something from that. What I need to remove is the area underneath the lower function. So if I find that area, the integral from a to b underneath g of x, the parabola, the lower function, the bottom function, if I take the blue area and cut away the red area, what I'm going to be left with is precisely this green space. So top integral minus the bottom integral. That's basically what this is saying right here. Procedurally, how can we do this? First, identify which function is the top and which function is the bottom. That's not quite as straightforward as you might think. Then identify the intersection points. Where are the exact numbers for a and b that you have the two functions crossing? That might require a calculator, as we'll see. Set up your integral, as we saw on the previous screen. Top minus bottom is your ruling paradigm. And then once you have an integral, just solve it. Either solve it by hand using the skill we learned last class, skill R, or use a calculator to solve. So we'll look at examples of both. Okay, in our first example here, we have the region R. It's bounded by the functions f of x, negative x squared, and g of x, 3x squared minus 8x. Find the exact area of the region without using a calculator. Okay, so step one, identify which functions, which upper and lower, top and bottom. So it looks like because f of x is a negatively oriented parabola, that means that f of x is this function right here. And because g of x is a positively oriented parabola, 3x squared minus 8x, that should be this function here. So this one right here is g, and this function here is f. So we have our top and our bottom. Our top function is f, and our bottom function is g. Okay. Second step is to find the intersection points. Well, one of the intersection points looks like it's fairly obvious. It looks like it's 0. The other intersection point looks like it should be 2. So now I have A and B. So to find the area of this region here, all we have to do is set up the following integral. This integral is going to be the integral from A to B, 0 to 2 in this case, of my top function, f of x, and f of x is defined as negative x squared, f of x minus the bottom function g of x. I'm going to use parentheses here to be precise. I'm subtracting all of g of x dx. Top minus bottom. So we have our integral here. We've set it up. That was step 3, I think. Can't count. And all it remains now is to solve. So let's solve this thing by hand. So I'm going to go ahead and distribute this negative. And it looks like I can simplify this before I take the antiderivative. Negative 4. Okay. Let's go ahead and take the antiderivative of this. So this should feel familiar in terms of skill R. Double check that, looks okay. Plug in 2, plug in 0, and subtract. So plug in 2. Plug in 0. Okay. 2 cubed is 8. Negative 32 over 3 plus 2 squared is 4, plus 4 is 16. That's 0, that's 0, that's 0, that's 0. Over here, negative 32 over 3 plus 16. Negative 32 over 3 plus 16 is 48 thirds. Subtract and you get 16 thirds, which is the answer. That's the number of blocks that are shaded in, basically. Let's take stock of what we did, identified which function was which, identified our intersection points while looking at the graph, setting up our integral, again, top minus bottom, solving the integral we've set up using skills we've learned before. Now, next example here right away looks pretty funky because we don't have a single region, we have 2. And that's kind of complicated. So let's read this problem carefully. It says we have f, negative x squared plus 9, and g, negative 1.25x plus 7. So one's a curve and one's a line, so that's pretty straightforward. My curve here is, I'm going to call it f of x, and my line here is g of x. So this is g. Now, in order to find the shaded area, what I want you to recognize is which function is the top changes. Let's take a look at this first region here. Let's call this region R, and let's call this region S. In region R, which function, f or g, is the top function? Right, so that should be f. So our integral here should be f minus g over here. Top function minus bottom function. But in my other area, this little region over here, now the top function is that straight line. The upper function is g. So in this region, I should find g minus f. In both instances, I'm doing top minus bottom, but which function is the top differs, right? Okay, so we identified which function's top, which function's bottom. The next part is to identify my intersection points or my boundaries. Now, right away, you can tell based on our earlier analysis that this is going to require two integrals. So if we look at region R has one boundary that's very clearly 0, another boundary that's not really clear at all. I don't really know what that number is. I can zoom in and maybe guess. It looks like 2.2-ish, 2.3 maybe for the x value, but it's hard to be sure. So we're going to find what that value is in just a moment. So it's from 0 up to some unknown value for now, and we're integrating f minus g, which is negative x squared plus 9f, use parentheses to be sure, minus g, well, g is negative 1.25 x plus 7. So there's that. So how do we find this intersection point? This is where we're going to use a little bit of technology, namely the TI-84 calculator. So I'm going to pull up my TI-84 here. And in my y equals, I'm going to type in my two functions. So my first function is negative x squared plus 9. And my bottom function is this. I'm going to graph those. So what I'm looking for is this intersection point right here. I want to find where that crosses. You may remember this from an earlier math class. There's a way to find the intersection between two curves, and that is to go to the second trace menu, or the calc menu. Second trace. And then choice 5 is intersect. So I'm going to choose that. It first asks for the first curve. I'm actually going to move my cursor close to where I want it to be. I'm going to press enter. Second curve, yep. And again, make sure your cursor is near where you want it to be when it asks for guess. The intersection point has an x value of 2.71. Sorry, 2.171. 2.171. So we now know that this is 2.171. So we're going to go ahead and find this integral. Doing it by hand is pretty tough, but we're going to use the calculator to make this a lot easier because we're allowed to in this problem. Go back to the home menu. As you know, the way to check a definite integral is to go to Math 9. We're integrating from 0 up to 2. Negative x squared plus 9 minus, use parentheses, negative 1.25 x plus 7. With respect to x, and the area of region R is approximately 3.877 units. So going back here for a moment, 3.877 units. For region S, we have the following. Region S is picking up from 2.171. That's the left boundary of region S. Up to my right boundary, which is given to me as x equals 3. So from 2.171 up to 3. This time my top function is the linear function. So negative 1.25 x plus 7 minus the bottom function, which in this case is the parabola, which was negative x squared plus 9 with respect to x. So let's go ahead and type that in the calculator. I'm going to show you a bit of a shortcut here. It's not much of a shortcut, but it might help. So currently in my Y1 menu, I have f as negative x squared plus 9 in the Y1 slot, and g, the linear function, in the Y2 slot. So in calculator language, g minus f, which is what I want, is y2 minus y1. This function minus that function. So I've already typed it in here. So when I go to type it in here, I don't have to type them in again. I can just type in the following. I can hit alpha trace, and I can do y2 minus alpha trace y1. So in the calculator's point of view, y2 and y1 are those functions that are entered in y equals. Therefore, it's doing exactly this operation in the calculator. And we get a smaller answer because it's a smaller area, 1.252. So the actual ultimate question was the total area. So we just add these together, 3.877 plus 1.252. Completely failed at typing that. And we get 5.129. That's our answer. So we'll do some more examples, and I will see you in class later this week. Hope you're doing well. Bye-bye.